the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students and pre-calculus students who are going through matrix multiplication, or at least the arithmetic of matrices. In this video, we'll focus on matrix multiplication itself, so get ready, it's a wild ride. Start with an example here. Consider the M by N matrix A and the N by P matrix B, and then the vector X, which is in RP. Now that's a lot of letters there, but hopefully that makes sense to you. We'll start by writing the vector B times X as a linear combination of the columns of B. And this is to set up the idea of what matrix multiplication actually is. So I'm stepping us through the process. We already know that matrix vector multiplication is just going to be a linear combination of the columns of the matrix B with weights, the entries in X. Now I should probably make sure I know how many columns the matrix B has. And we can see right here, the matrix B has N rows and P columns. So we'll go ahead and write out the P columns of the matrix B. And that works out actually very nicely because we were told that X is a vector in RP, so it only has P entries. And that matches up with what we have here. So there we have it. B times the vector X is written as a linear combination of the columns of B. Now we're going to go ahead and write the vector A times Bx as a linear combination of vectors. Now notice I didn't say linear combination of vectors in some type of matrix or whatever, because I want us to actually naturally explore this. Now you may think we're about to do a matrix multiplication because it looks like we will, but actually we're not. Remember, Bx, this guy right here, is just a vector. You're summing up x sub 1 times the vector b1 plus x sub 2 times the vector b2, and so on and so forth, all the way to x sub p times the vector b sub p. However, I'm going to leave it just as a summation of vectors for a very special reason. And that is because we happen to have a property way back when, it's called Theorem 5 in the textbook that I use, but the property says the following: that a matrix A times the sum of vectors is actually A times the first vector plus A times the second vector. Now, I should mention, this is if the multiplications are well defined. That is, the number of entries in these vectors is the same as the number of columns in the matrix A. As long as that is true, we can go ahead and say this property is true. Also, if you have a matrix A times a constant multiple or a scalar multiple of a vector, and again, if the product is well defined, then that's the same as the constant or the scalar times the product of the matrix and the vector itself. We're going to use those two properties together right here. This is a matrix A, and it's multiplying the sum of a bunch of vectors. Just performing that blue ink right here multiple times, we get down to this piece right here. And remember, all those x sub i's, they're just scalars. So I'm going to go ahead and use that property again in blue ink right here. Let's go ahead and do that. And we know how to rewrite this multiplication, actually, this linear combination of vectors, as a matrix vector product. And in fact, that's what part C is stating right here. Use part B to conjecture a formula for the product of two matrices A and B. If you just realize that that's a linear combination of the columns of a matrix, we could write this as the matrix AB sub 1, AB sub 2, all the way to AB sub p times the vector X. This is from our previous knowledge of linear combinations of vectors being written as a matrix times a vector with the weights of those linear combinations as its entries. Now, this doesn't actually give us a obvious conjecture maybe, but let's go ahead and make a conjecture about the matrix product A times B. Well, if you take a look at part B, we have A, the matrix, times the quantity B times the vector X. And a lot of people will say, I bet you that's probably the same thing as AB times the vector x. Now, we do not have a theorem that states that right now, but that is actually true. So the conjecture we might want to state is the product AB is the matrix whose columns are the vectors AB1, AB2, all the way to AB sub P. That's a really nice way to think of matrix-matrix multiplication. And it is actually true. That is actually what the matrix-matrix multiplication is. It's just a matrix where the column vectors are the first matrix times each respective column of the second matrix. Now, looking at part D here, what are the restrictions on A and B so that the product AB is well defined? Well, if you look at this matrix-matrix multiplication right here, you can see that from this statement right here, the number of entries in B sub 1 has to match the number of columns in A. That's from just basic matrix vector multiplication. Let me write that down below. And I wrote it this way: the number of rows of B must match the number of columns of A. The reason why I say the number of rows of B is because the number of entries in the first column of B is actually the number of rows of B. So the number of rows that B has is the same, or should be the same, as the number of columns that A has. And that is actually the restriction on matrix-matrix multiplication. So if you have two matrices multiplying, A and B, and let's just pretend it's an M by N matrix, and let's pretend that B is H by K, then if this product is going to be well defined, you better believe N should equal H. Those two inner sizes should match. If they don't match, then the number of rows of B does not match the number of columns of A, and therefore these multiplications right here are not going to work. Remember, a matrix times a vector works like this. It will be the linear combination of the columns of the matrix A with weights given by the entries, the corresponding entries in that vector B sub 1. Well, we know that A has n columns from the definition up here, and therefore the number of rows for B had better be the same, and it is. In this case, that works out perfectly. Now, as an aside, not very much of an aside, this is actually somewhat required, let's see what the ending dimensions are going to be. Notice how many columns our resulting matrix has. 1, 2, 3, 4, 5, 6, all the way up to P. So this is a something by P matrix, and we'd like to know how many rows this matrix product has. Well, that's going to match the number of rows that A has, because again, these vectors right here are going to be a linear combination of the columns of A, and the columns of A each have M entries. And look what happens. When we have A, which is an M by N, times B, which was told to us to be an N by P matrix, in the end, we get a matrix, I'll call it C, but the inner dimensions match up, so they link together, and the result is an M by P matrix. You keep the outer dimensions. It's a cool way of thinking about it. To formalize this, let's take a look at a definition here of actual matrix multiplication. If A is an M by N matrix and B is an N by P matrix, then the matrix product of A and B is defined to be this matrix right here. Notice it matches what we wrote in the previous example. Now remember, in the previous example, I said, well, it looks like that's what it should be. I didn't actually say that's what it was. I said it looks like it should be that. It seems fairly convincing, but we needed somebody to come along and say, by the way, that is actually how we're going to go ahead and define it, and here it is. And the resulting matrix is M by P. In other words, it's the outer dimensions of that product. Now, something you should see immediately from this definition. This matrix multiplication is well defined. The inner dimensions or inner sizes match, and this will be some resulting matrix M by P. However, commutativity for matrix multiplication is not necessarily an existent property. That is, this product right here will not work if M and P are not the same values. So this is just a heads up. I'm just going to cross this out, that in general, A times B is not going to be B times A. And in fact, if one of those products is well defined, the other one might not even exist, might not be well defined. So this is your first example, and a really good example, of a multiplication in mathematics that does not commute. And believe it or not, that's very, very important. And it commonly happens as you move forward in mathematics, that you learn different structures where commutativity of multiplication just does not exist. And I have this single clarification here because I really want to drive the point home. The ith column of AB is A times the ith column of B. And it's a linear combination of the columns of A using the entries from the ith column of B as weights. That is, the matrix vector product AB sub I, which is actually just the ith column of the product AB, is this linear combination right here. Now that linear combination is very bulky. Don't get me wrong. That's not the approach I want to focus on right now, but it is very true. That is actually the ith column of A times B. And again, I don't want to view it that way right now. We'll come back to this later on. So now we're at our first kind of real example in this section, and it's just, let's multiply some matrices. So let's make some up. And you could actually pause the video, make up whatever you want. Just remember, when you group together or start to multiply matrices, their inner sizes must match. All right, I've thrown down some matrices here. The best thing to do actually is to write their sizes next to them. I usually write it to the bottom right-hand side of each matrix. So this is a 2 by 3, and the next one here is a 2 by 2, and then C is a 3 by 2, D is a 2 by 4, and finally E is a 2 by 2. You could do all sorts of multiplications here. So let's write down all the possible combinations. The good products, well, I'll start with A. A is a 2 by 3. Whatever I multiply it against has to be a 3 by something. And the only one that is a 3 by something is C. In fact, let me go ahead and write that A is a 2 by 3. C is a 3 by 2. The inner sizes match. So therefore that product is actually going to be a 2 by 2 matrix. Let's also look at, I haven't multiplied them yet, but let's go ahead and look at other ones. Let's look at what B can multiply. Well, B is a 2 by 2. It can actually multiply A. It could also multiply D. Finally, it can multiply E. Now let's look at C. C is a 3 by 2. It can multiply A. Now, I want you to notice something about C times A versus A times C. When I multiply A times C, the resulting matrix will be a 2 by 2 matrix. If I multiply it the other way around, C times A, the resulting matrix will be a 3 by 3 matrix. So this should really be convincing that matrix multiplication is not commutative. It might exist, like A times C and C times A both exist, but they're not the same result, or they don't represent the same matrices. All right, let's see what else we can multiply C against. We can multiply it against B. We could also multiply it against D. And finally, we can multiply it against E. Now, something I just saw that I didn't mention before, but when we're looking at all the products with B, technically, B can also multiply itself because the inner sizes match. A could not multiply itself because A is a 2 by 3. It can't multiply another 2 by 3 because the inner sizes do not match. C cannot multiply itself because it's a 3 by 2. No way that it can also multiply another 3 by 2. It just can't work like that. Let's take a look at what D can multiply. Well, D is a 2 by 4. And unfortunately, there are no 4 by anythings here. So D can't multiply any of these matrices. So I erase that. And then finally, E. Well, E can multiply A. It can multiply B. It can multiply D. And it can multiply itself. So let's take a subset of these and actually do those multiplications. I really would like to see what AC and CA look like just to show you that they're not the same. I also want to take a look at, let's do a B squared here. And let's look at B times E and E times B. That would also be very helpful. And we haven't picked on D, so let's do this one right here. That's quite a few multiplications. Once you see the first one, the rest are pretty fast. So A times C. Well, We know by definition this is going to be the matrix A times the respective columns of C. Notice I only wrote C1 and C2 because C actually only has 2 columns. The result should be a 2 by 2. Let's see what happens when we do this. Now, honestly, there's a lot of busyness with the multiplication here. And so what I generally do when I'm doing this style of problem is I go ahead and write the multiplications off to the side so that we can actually see things. I'm going to scoot things over to the left a little bit to give myself some room. And I'll stick with my red ink here. So I'm going to figure out off to the side what A times column 1 of C looks like. And remember, we've had a conversation about multiplying matrices times vectors in the past. And I personally like to think of the product as dot products of this column vector with the rows here. So that's how I'm going to do my matrix vector multiplication. Just visualize that this vector is laying on its side. We have 2 times 1 plus -1 times 3 plus 4 times a -1. You should be pretty decent with that now, so I'm not going to actually do all the sub mathematics. I'll just condense it right now. And then I do the same thing for the second row. 2 times 0 plus -1 times 1 plus 4 times 2. And there we have it. That is the product of A and column 1 of C. So I'll just write that down over here. And finally, the product of A and column 2 of C. And actually what I'm going to do is go ahead and erase my work here and fill in column 2 of C. There we have it, 310. Notice that product ended up being a 2 by 2 matrix, which is exactly what we said A times C should be. The result should be a 2 by 2 matrix. Let's go ahead and deal with C times A. So I'm going to go ahead and maybe erase my highlighting there to say we're done with that. And I'll focus in on C times A. The result should be a 3 by 3. Let's see what happens. Again, it's a matrix where the columns are the products of C and the respective columns of A. And remember, A only has 3 columns. Off to the side, there's C. Now let's go ahead and multiply that by the first column of A. Now notice how quickly I did that. Even though I always fast forward my computations here, you should note I actually did that just as quickly as the fast forward happened. It's because this vector right here, when used as a dot product, really only keeps the first entry, 2, -1, and 4. It turns off the second entry. So that was a pretty easy product. I'll go ahead and fill that in. And now we're off to C times A sub 2. A sub 2 is not going to be so pretty. It's just 3, 1. 1, 0 is much cleaner, but 3, 1 will be fine. Let's go ahead and do that product. All right, so 7, -1, 16. I'll use that as my second row. And finally, C times A sub 3. 0, 5, 4. Now you do have to be kind of careful with matrix arithmetic because there's a lot of arithmetic involved. It's very arithmetic heavy. So there is a lot of room for mistakes. Watch your arithmetic throughout. I could likely make mistakes in this video, so I have to be incredibly careful. Notice C times A is a 3 by 3. A times C is a 2 by 2. They're definitely not equal. Now I'm completely done with that. Honestly, I think I'm driving the point home and going kind of nutty here. So let's go ahead and do maybe B squared or B times B. And we'll go ahead and leave out the C times D. We've already done stuff like that. We'll do B times B and then BE and EB. And we can do these somewhat quickly. Let's do BE and EB very quickly. Again, E only has 2 columns, so it's just 2 column vectors in B times E. Going up to my scratch area, what you're looking at here is the matrix B times the first column of E. Now I'm not even going to help you visualize, I'm just going to do the mathematics. Very nice, so that's 1, -6. I'll go ahead and write that in there. And now let's take the second column of E. And that'll be -1, 1. Very fast computation. Great. That's a 2 by 2 matrix BE. Now let's take a look at the 2 by 2 matrix EB, which again is a matrix where the columns are EB1 and EB2. Going up here and replacing my scratch work, that is the matrix E times the first column of B, doing the multiplication very quickly. We have 4, -1, and now we'll multiply by the second column of B. 3, -2. So BE is the blue matrix and EB is the black matrix. They're both 2x2s, but they're definitely not the same matrices. So again, great justification that commutativity in general is not going to hold with matrix multiplication. It'd be good if I actually wrote that in the proper order. Finally, let's just go ahead and do B squared here. And the notation that does get used is actually that right there, B squared. It's just a common notation all throughout mathematics. It's very common to think that when you square a matrix, it just squares all of the entries within the matrix. That is not true. So let's take a look at what B times the first column of B looks like. We get -1, -4. Now B times the second column of B. We get 8, 7, barring any arithmetic mistakes. Notice that this is not equal to had you squared every entry in B. Remember, B is 1, 2, -1, 3. So 1 squared would be 1, 2 squared is 4, -1 squared would be 1, and what did I say, 3? Yeah, 3 squared would be 9. Notice this is not the same as the actual squaring of the elements. So do not think that B squared means, oh, I'll just square everything. That's not true. It's actually B times B, and that's completely different. Now, as I've mentioned, I just want to make the point in red here. Matrix multiplication is not commutative in general. That is, AB is not equal to BA. Now, there are times when that actually is true, but in general, it's not. And we'll deal with those times where it is true a little bit later on. Now, this is more of a concept question that you'd run into in a textbook or something like that. And it's just stating that if you have a vector y that's a linear combination of the columns of AB, then y must be a linear combination of the columns of A. Let's start with the assumption that y is a linear combination of the columns of AB. Well, remember, the columns of AB are the matrix A times the corresponding columns of the matrix B. And here I'm assuming that A is m by n and B is n by p. It wasn't explicitly stated, but since they did say that y, the vector, is a linear combination of the columns of A times B, that just basically means that the product AB is defined. Well, that will imply that y is some combination, let's just say it's C1 AB1 plus C2 AB2 plus so on and so forth down the line. That's a linear combination of the columns of A times B. And we want to show that that means that y is a linear combination of the columns of A. Well, this is going to get a little bit messy, I hope you don't mind, but we happen to know, if I zoom in here, that this matrix vector product A times B sub 1 is just a linear combination of the columns of A. In fact, and I'll use, I guess I'll use black for this specific one. Now remember, the matrix A has n columns. I'm just saying it's an m by n matrix. So this linear combination, and it's only, that black ink is only for this product right here. That linear combination, well, it will have n entries or n elements because there are n columns in A. That should also make sense because B is an n by p matrix. And so it has n rows. So each of these column vectors, specifically B sub 1, has n entries. 1, 2, all the way to n. And you should notice that I labeled those B sub 1, 1, B sub 2, 1, all the way to B sub n 1. It's the first row of B from the first column. And then the second row of B, again, from the first column, because we're dealing with the first column vector of B, all the way to the nth row of B from this first column. Again, because we're dealing with the first column of B. Now I'm going to move on to C sub 2 times A B sub 2, and this time I'll do that in green. Well, A times B sub 2 is a linear combination of the columns of A with weights the entries of B sub 2. B sub 2 is the second column of B. Notice the structure of this. Again, I'm dealing with this product right here. The structure is very, very similar to the structure from this right here. We have a linear combination of the columns of A, where the weights are the entries in the second column of B. Notice this says first row, second column of B, second row, but still the second column of B, all the way to the nth row, second column of B. So these are the entries from the second column of B. And this summation continues until you get to this product, which again, A times B sub P is just a linear combination of the columns of A with weights from the pth column of B. Notice how I've written it. Again, we have the first column of A times the first row but the pth column of B. So the entry from the first row but pth column. Again, the second column of A times the entry from the second row but pth column of B. Again, because you're multiplying by the pth column of B here. All the way down to the nth row but pth column of B times the nth vector, column vector in A. I should also note, we ended with B sub np, and B is an n by p matrix. That will match up very nicely. Now remember, the ultimate goal here is to prove, or to show, I should say, that Y must be a linear combination of the columns of A. We're saying that Y is equal to all this stuff right here, C1, A, B1, and so on and so forth, which is equal to this colorful ink right here. And now we're going to reorganize things. I'm going to collect like vectors. So vectors A1 I'll collect up. There we go. I just basically grabbed all of those vectors A1 and their corresponding coefficients. C11B or C1B11, C2B12, there'll be a C3B13, and so on and so forth, all the way to CPB1P. Plus, now I'll go to the second vector, A sub 2. So those vectors right there. We'll collect up all their coefficients, we'll factor out A sub 2, and you get the following. There we have that. Notice, by the way, these are all from the second row of B. B, second row, column 1, second row, column 2, second row, column P. And we continue that forward until we get down to the vector A sub n, collecting up all the coefficients of that. And notice what we get. This is just a sum of scalar multiples of the vectors, the column vectors from A. Some number times A1, some number times A2, all the way down to some number times AN. And that is a linear combination of the columns of A. Now, as you can see, something like this is a bit bulky, right? I mean, I did it in a short amount of paper, but the reality is it's a lot of notation. So you do have to get used to heavy notation when you deal with matrices. There's no avoiding it, really. Honestly, the best way to shorthand matrix multiplication would be like this. A times B is just some big old matrix where each column is just A times the first column of B, and the second column is A times the second column of B, and so on and so forth. However, there'll be many times when you can't use that shorthand. You have to use this double subscript notation that I have going on here. That's just a reality that we have to get used to. Now, here is a nice recipe for a faster method for computing the ijth entry of a product of matrices. And this is something usually you would prove in a homework assignment, something like that, so I'll leave it to you. But the ijth entry of the product of AB is just a dot product of the ith row of A with the jth column of B. That is, the ijth entry of AB is just this mess right here. Now, I gotta be honest with you. A lot of people don't memorize this notation, they just do it. And I'll show you how that is done right now. We'll go ahead and go back and collect some of the matrices we used in a previous example, specifically this example right here. I'm just going to rally up these matrices, and I'll just remind you that we computed the products AC, CA, BE, EB, and B squared. Now, I don't want to go through and do all those, but let's do AC. And the best way to show this is really to actually write the matrices out. Now, the method we're about to use uses dot products the entire time. The resulting matrix, since this is a 2x3 and a 3x2, the resulting matrix should be a 2x2 matrix. Now, I left this matrix somewhat large because I just want to showcase the mathematics first, and then we'll kind of clean it up. In the first row, first column of our resultant matrix, we're going to take this first row times this first column. And when I say times, I mean the scalar product or the dot product. So if you can imagine the dot product between those two rows or lists of numbers, it's going to be 2 minus 3 minus 4. And I wrote it right there just because I want you to know kind of where it came from. It's 2 times 1, negative 1 times 3, and 4 times the negative 1. In row 1, column 2, again, I'm going to highlight row 1 and multiply it by column 2. And again, when I say multiply by, I truly mean the scalar product or the dot product. And this time, let me go ahead and clean up this number here. 2 minus 7 is a negative 5. And let's take a look at what this is. 1 plus 6 minus 4. That's 7 minus 4, which is 3. Now we move on to row 2. Notice that I just highlighted row 2 because we're now looking at the results in row 2. So the row that you're working in will match the row of the first matrix. The column you're working in will match the column of the second matrix. So we're in row 2, column 1. 2 times 0 plus negative 1 times 1 plus 4 times 2. That's 0 minus 1, which is negative 1, plus 8, which is 7. And finally, getting that entry in row 2, column 2, I'll highlight row 2, column 2, and do the scalar product or the dot product. And that's just going to be 0 plus 2, which is 2, plus 8, which is 10. So we get negative 5, 3, 7, 10, and we can actually go back and check to see that that is correct, and that's what we got earlier, negative 5, 3, 7, 10. Although when we did that, we had to do all this side work along the edge to do our mathematics. But here, we've just introduced a little bit of a better method, although I have to say it is still computationally heavy. That's just how it is with matrix multiplications. Now, there's really no reason for us to go through and do a ton of them, but let's just do one that we didn't do last time. Instead of going through and doing all those, let's just do one that we didn't touch last time. Let's do C times D. Now that matrix multiplication is well defined because C is a 3 by 2, D is a 2 by 4. The result will be a 3 by 4. So I'm just putting in a big bracket there just because I know it's going to be somewhat of a larger matrix. And then I go through and I actually do my row times columns, right? Row 1, column 1, that's 4 plus 1 or 5. Row 1 times column 2, that's going to be 2 plus 1, which is 3. Row 1, column 3, well actually that's 0 plus 0, that's kind of nice. And finally in row 1, we have row 1 times column 4. That's 8 plus 1 or 9. Now we move on to row 2, and that's going to be what? Negative 2 plus 2, 0. Row 2 times column 2, that's negative 1 plus 2, which is 1. Row 2 times column 3, that's 0 plus 0, which is 0. And by the way, you start seeing these cool things like, man, if I ever have to multiply by the 0 vector, I'm going to be happy, right? Because it just zeroes things out. So you start noticing those. Those aren't things that I'm going to really build theorems for. I mean, they have been built in the past, but they're just things that you need to notice as you do a lot of matrix multiplications, that there are certain vector products or dot products that are nicer than others. And the ones that are nicer than others are the ones full of zeros. And that sounded weird. It should be the vectors full of zeros because ones and zeros sounds odd. All right, continuing forward, row 2 times column 4, we have -4 plus 2, which is a -2. Finally, row 3, column 1. That's 8 plus 4 is 12. Row 3, column 2, 4 plus 4 is 8. Row 3, column 3, well, that's 0 plus 0 again, so that's just 0. Notice what happened to our column 3 here. It's all zeros because our column 3 there was all zeros. And finally, row 3, column 4. That's 16 plus 4 is 20. And there we have it. That is our resultant matrix, our product. Nice looking matrix actually for many reasons, but there you go. That's very beautiful. Love it. Not too bad to compute. So I highly recommend that you take this idea and just write your own matrices, make up a ton of examples. That's all you really have to do. Practice makes better. Never perfect, but better. Before we leave this video, I want to remind you of something from our previous work, specifically transformations. If A is the m by n standard matrix for the linear transformation T, and B is the n by p standard matrix for the linear transformation U, and X is any vector in Rp, then the composition of the linear transformation T with the linear transformation U acting upon the vector X, remember, the standard matrix for T is A, the standard matrix for U is B. That's actually going to be A times B times X. The proof is actually not bad. By definition, U acting upon X is the same thing as B times X, and the transformation T acting upon that vector is A times, well, that vector. But we've actually shown early on in this video that A times the vector BX is actually a linear combination of the vectors AB1, AB2, all the way to ABP, which by the way, is this right here, the matrix AB1, AB2, all the way to ABPX, and that is by definition A times B. We define that right here. So because we defined it right here, I happen to know that ABX is the same thing as AB times X. So we have already actually proven that, which means that this supposedly gnarly proof is actually not much work at all. We just get right down to there and we're done. Now, the only reason why I introduced that here is because you've already dealt with linear transformations. It'd be nice to know, well, if we felt like transformations were sort of like functions before, we've been able to do compositions of functions in previous courses. Can you do compositions of transformations? And the answer is yep, you sure can. It ends up being a product of their standard matrices. All right, that's all I'm going to do in this video. I've been recording for quite some time today, so I think I'll stop. I hope that linear algebra is not too terrible for you, and I hope that I somehow ease your pain through the journey and the beautiful subject of linear algebra. Have a great day and be great humans.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause they are and work together until you feel at peace. Just listen close. Don't talk too much. That isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just